Hey guys, we've got a quiz on Tuesday about limits, so I figured I'd walk you through definitely the first 15 of these problems that I said were mandatory. And I'm pretty tired, but if I feel up to it, I'll walk through the other 18 as well for practice, just to give you a real good look at all the different types of limits that we're going to need to master. But let me go ahead and just jump in with number 1 and 2. Both 1 and 2 I hope you found to be pretty easy because, well, both of these can be solved just by that method of direct substitution. So looking at this limit, this is just some quadratic. It's continuous when x is 2, so I should be able to just plug in 2, so I will. And I get 2 squared. That's a 2 minus 4, so -2. That's my limit, and that's all there is to it. For the next one, this is a radical function. That guy's continuous, so as long as 1 is in the domain of this function, we can just substitute in, we'll get an answer. And of course 1 is in our domain, because 1 plus 4 is 5, so your final answer is just that the limit is root 5. That's it. 3, I think, is the first one where if we try to substitute in, then we do get that indeterminate form of 0 over 0. I would still recommend you check it out. Like, let's just see what happens. But of course, yeah, if I plug in 0, I get a third minus a third. Now, getting 0 in the numerator isn't bad. But of course, we plug 0 into the denominator. That's also 0. So this is for sure 0 over 0, which tells me I need to go back to the beginning and use some kind of algebraic strategy to simplify the expression I was given to end up with something that will not give the indeterminate form anymore. And so for this, I see a compound fraction, and that tells me that I want to get a common denominator. So if I'm taking the limit of this whole thing, then on the top in the numerator, I'm going to want to get that common denominator, like I said. That least common denominator that I'm after is just going to be some expression that has a factor of 3 in it, for sure. Also a factor of x plus 3 in it, for sure. So this is the LCD we're trying to chase down. So looking at the top, this first fraction you'd multiply by 3 over 3. That would give you 3 over 3 times x plus 3. In the second one, we have to multiply by x plus 3 over x plus 3. So all that is just in our numerator. Our denominator is still x. But that's the first step in trying to run this thing down. So now, what do we get? We now have the limit as x approaches 0 of, in the numerator, we're going to get this big fraction. We're going to just keep that denominator though, the 3x plus 3. So that means in the numerator we're going to get 3. Now, super important, a lot of people made this mistake. I'm subtracting this whole binomial. So distribute that negative in, and this becomes 3 minus x minus 3. And then this whole thing will be all over x. But now from here we can see that the 3 minus 3 will just cancel out, leave us with a factor of negative x in the numerator. So we've got negative x over 3 times x plus 3. And again, I strongly encourage you, just think of this x that's in the denominator as x over 1, and then think of this whole thing as a big division problem with this as your division sign. So when it comes time to simplify, just turn this big division problem into a multiplication problem where you're multiplying by the reciprocal of the denominator. So we're going to take this numerator multiplied by the reciprocal of the denominator, so 1 over x, and then we'll happily cancel this factor of x and this factor of x. Notice I do still have a negative. So we're now being asked to find the limit as x approaches 0 of negative 1 over 3 times x plus 3. And that can now be solved by direct substitution, because the factor that would have given us trouble, the x, is gone. So final answer is we're going to get negative 1 over 3 times 0 plus 3, so 3 times 3, so 9. And I don't like my fractions to have negatives attached to the numerator or the denominator. You should be giving me a 1/9 that is negative. So I've attached the negative to the whole fraction. But there you go. That's number 3. And I put 4 on this page, I guess because it's fairly simple. It's not, yeah, okay. So 4 is weird. It's not an indeterminate case. If we plug in 1, then we get 1 squared plus 1 minus 30. That's 2 take away 30, so negative 28. Now in the denominator, 1 minus 1 is giving us 0. So I talked about this to a lot of people, but I'm not sure if everybody heard the message yet, so I'll say it loud and clear right now. What we're getting here, the negative 28 over 0, that's undefined. And when you plug into a function and you get an answer that's undefined, that typically means what you're looking at is a vertical asymptote, right? And so now think about that graphically. If you had some graph that had a vertical asymptote, then like 9 times out of 10, that means that as you approach from one side, you get a limit that goes to infinity. But as you approach from the other side, you get a limit that goes to negative infinity. And we know that that implies that the limit does not exist. So yes, what I'm trying to say is, as soon as you plug in and you get a 0 in your denominator, but not a 0 in your numerator, and that's not the indeterminate case, that just means that this limit does not exist. And I wouldn't jump through any hoops to do any extra math here. If you did factor the numerator, you're not going to get a factor of x minus 1 because we didn't get 0 when we plugged in 1. The only way to get a factor of x minus 1 is if plugging in 1 actually gives you 0, which it doesn't. You could just factor this and see that too. When we factor this, we're just going to get a 5 and a 6. We're going to get an x plus 6 and an x minus 5. So we see that factor of x minus 1 has nobody to cancel with. That means we do get a vertical asymptote. That means we don't get a limit. We just does not, the limit just does not exist. Okay, 5. All right, so this is now one of our other kinds of limits where you've got this radical. And if you try to plug in 7, then you'll get root 16, which is 4 minus 4, so 0. Plugging in 7 in the denominator obviously gives 0. So this is the indeterminate form. And the way that you handle these guys that have radicals is to multiply by the conjugate of the radical expression. So I'll take the root x plus 9 and the 4, but I'll switch the sign in the middle to a plus. And I'll do this to the top and the bottom. And we're multiplying. So we're now doing this limit. Let's clean this up and see what happens. We should already know what's going to happen. What is going to happen is the x minus 7 in the denominator, it's going to cancel with an x minus 7 that we end up with in the numerator. We hope. That's what we hope. So let's do this. Limit as x goes to 7 of. Now in the numerator, this is a binomial and a binomial, so we're foiling. So I'll do this entire radical times this entire radical, and I'll get the radicand, the x plus 9 with the radical going away. Then I'll get a minus 4 times the radical and a plus 4 times the radical. So those middle terms cancel. So I'm telling you, you don't have to write that math out anymore. I'm not gonna. But up top, we now have the last times the last. That'll be a minus 16. Any guesses as to what positive 9 take away 16 is, by the way? Hint, it's negative 7. So downstairs, we've got an x minus 7 times this whole, I forget the word, conjugate, root x plus 9 plus 4. Okay, so this means that up top, I'm going to be a little lazy here and say, this of course would simplify to x minus 7. And that does mean that we could cancel those. And so that brings us down to a new limit expression that is nothing more than the limit as x goes to 7 of 1 over our little conjugate, root x plus 9 plus 4. And that is an expression we can just substitute into, so we will. We get 1 over root 7 plus 9 plus 4. And that's 1 over, and you can decide for yourself how much work you want to show here. I'm going to go ahead and just let this be a root 16 plus a 4. That's 4 plus 4, that's 8. So 1/8 should be the limit in question for number 5. So there it is. 6. Okay, 6 is a pretty good one. 6 is actually really quite easy once you see what you have to do. We can see that plugging in 0 does give us 0 plus 0 over 0. It's going to be the indeterminate form. But we also should notice that this first term here has 5 x's in it. The second term has 4 x's in it. Sounds like we've got a common factor of x to the 4th, which we can pop out to be left with a 2x plus 3. And then very conveniently, in the denominator, we also have a factor of x to the 4th. And those guys cancel each other out, x to the 4th, x to the 4th. So we now have a pretty simple limit. It's just the limit as x goes to 0 of 2x plus 3. Which, of course, we can just substitute right into. So this is 2 times 0 plus 3, which is 0 plus 3, so 3. And that's it. What about 7? Aha. So 7 is another complex fraction problem. Now, do I have to actually simplify it? I think there's another problem in this set lurking that we don't have to do any algebra for. We could just use direct substitution. And I think it is this one. Because if we plug into the numerator, don't we get 6 up there? And when we plug into the denominator, we get 1/12, take away 1/6. That's not really giving off 0 vibes, is it? This is giving off something other than 0 vibes. So what is this? This is 6 over 1/12 minus, let's see, hit this with a 2 over 2. That's going to give you a 2/12. And there's your common denominator. So this is a 6. Now technically it's 6 over 1. So I may start including that over 1 now because we're getting closer to our final complex fraction form. So this is negative 1/12. But again, I'll always recommend that if you just treat this fraction bar as a division sign, then just do like you did in 3rd grade, where you take the 6 over 1, and instead of dividing by 1/12, you multiply by 12 ones. Now that's negative, who cares? So this is looking like a final answer of 72 over 1, aka just, now negative 72 of course, but whatever. But negative 72. This was another direct substitution problem. We did not have to try to combine these or use a conjugate or use any of our special fancy algebraic approaches. Okay, 8 is another easy one. I'm not liking this pattern. I'm starting to think too many of these problems were a little too simple. Alright, but look in here. It's just GCF again, like the one we saw a minute ago. In the numerator you can factor out an x to be left with an x minus 5. And then very conveniently you've got an x minus 5 in the denominator. So those cancel. And now you're just evaluating the limit as x goes to 5 of the very basic function x. And obviously if you plug 5 into that you get 5, so the answer is 5. That's it. Alright, 9 is honestly more of the same. For 9 it'll be the limit as x approaches negative 7, which will give 0 in the denominator. I'm not sure if it gives 0 in the numerator, but you know what? Let's just start factoring because we can. We can factor out an x first of all to be left with 2x squared plus 11x minus 21. This is all over x times x plus 7. Alright, so the one new thing we're getting to look at is factoring a quadratic that has a leading coefficient. And so what I might do, rather than being lazy, is I'll just take that quadratic, I'll kick it over the side, and I'll show work like I'm showing it on a piece of scrap paper. but the 2x squared plus 11x minus 21, if you multiply the first, the leading coefficient by the constant, you get negative 42. So we know it's factors of negative 42 that we want to look at, and those factors are 1 and 42, no help there, 2 and 21, that's no help, 3 and 14, and then that's the pair. If you want a positive 11, then let this 3 be negative, let the 14 be positive. Now that I've identified those correct factors, when I factor, I know that I'll need a factor of 2x and a factor of x. I also know that this 2 is going to multiply somebody to give me one of these factors. Now you can't do 2 times anything to get a 3, but you can sure as heck do a 2 times 7 to get after that 14, and to get a 3, well, this is just a 1. So when you do your inner products, you'll put a 3 here. 3 times 1 will give 3. I want that to be negative. I want that to be positive. There's your factored form. So now take this factored quadratic from over here in this work area, bring it back over here. So where are we? This would now be the limit. As x approaches negative 7 of an x times a 2x minus 3 times an x plus 7. And this is all over an x times an x plus 7. So it turns out we have 2 factors that cancel, because we've got the x plus 7 getting rid of the x plus 7. And now this isn't necessary, but we also have the x canceling out the x. So you may as well do it. And then all you have to do is evaluate the limit as x approaches negative 7 of 2x minus 3. Which of course, again, we can do by just substituting in. So this limit will be 2 times negative 7 minus 3. Negative 14, take away 3 more is negative 17. There it is. What about 10? Okay, so 10, it looks like we will probably have to combine the fractions. Let's find out. If I had 1/3 minus 1 over 3 times 1, yeah, that's a third. And 1 minus 1, yeah. So third minus a third is 0, and 1 minus 1 is 0. So we definitely have to clean up this expression. Let me clear the screen. Okay. All right, this one doesn't look bad. It looks pretty simple. In fact, it's so simple that to combine these fractions, I only have to multiply the first term by an x over an x to get to my LCD of 3x. So that means this fraction will be x over 3x minus 1 over 3x, and that's all over x minus 1. So again, from here, in the numerator, we're keeping our 3x denominator. Our numerator would just become x minus 1. And that whole thing is all over x minus 1. So it sure looks like those guys are going to cancel out. But remember, this guy would go over 1. We're now doing the limit as x approaches 1 of my numerator, the x minus 1 over 3x, times the reciprocal of the denominator, 1 over x minus 1. Which at this point, yes, it's quite clear that the x minus 1s do cancel. They sort of cross-reduce. And that gives you the final expression that we can evaluate. We've got the limit now as x goes to 1 of 1 over 3x. And again, we'll just directly substitute to get our answer. So plugging in 1 gives 1 over 3 times 1, aka 1/3. All right, that's 10 of these down in 20 minutes. That's not too bad. Let's keep going. All right, 11. So this is another radical one. Are we going to need the conjugate? I think so, because plugging in 0, yep, would give root 11 minus root 11. That's 0 over 0. So, okay, fine. We'll multiply this thing by its conjugate, which is root x plus 11 plus root 11. And if you do it to the top, you got to do it to the bottom. All right, so this will be the limit as x approaches 0 of, Now in the numerator we're foiling, so we're going to just get that radicand of x plus 11. Then we're going to get an outer term and an inner term that just cancel each other out. But the root 11 times the root 11 will give us a normal 11. And this will be all over x times this whole conjugate. So root x plus 11 plus root 11. Okay, and then if the 11 and the negative 11 can cancel, then that frees us up to go ahead and just let the x and the x cancel. And then we've got a evaluatable limit on our hands, because this is just going to be the limit as x goes to 0 of 1 over the entire conjugate, so root x plus 11 plus root 11. Alright, and plugging in 0 seems like it's just going to give me 1 over a root 11 plus another root 11, which of course is 1 over 2 root 11. Which of course is fine, but I don't know, I'm a little old school on this, I guess, but I would like to clean up the radical in the denominator. So if you multiply by root 11 over root 11, then you get root 11 over 2 times normal 11. So the final answer is root 11 over 22. And that's that. So let's do 12. Okay, 12. Is this just evaluatable? Plugging in 3? Yeah, it kind of is. Because if we just substitute in, we get 2 times 3 minus 6, but over 3. So yeah, that numerator is 0. We get 6 minus 6. We get root 0 over 3. But 0 over a number, that's not the indeterminate case. It's not even undefined. That's just 0. So that just means that this limit is literally just 0. Well, that's it. And that's fine. Not every single problem needs to require us to do all those extra steps. Some problems you can just substitute into, and that's it. So what about 13? Plugging in 0 would be the indeterminate case. So to clean this up, I guess we need to combine those. So this would become the limit as x approaches 0 of, I guess, 4 over 4x plus 2 squared. Because here I'm just multiplying by 4 over 4, but the other one is going to be x plus 2 all squared over 4 times x plus 2 squared. And never forget, this whole thing is still all over x. But we got our work cut out for us in the numerator. Okay, so the denominator of the numerator, that guy's fine. He's good to go. So it's going to be the limit as x approaches 0 of, now we've got this big old fraction bar. The denominator is x, and the denominator of what's upstairs is 4 times x plus 2 squared. Now in the denominator, I don't think I want to expand that out. I want to just leave that alone. But up top, I want to do 4 minus, but I need to be subtracting the expanded form of this binomial so that I can actually combine it with the 4, so that I might get something new that is factorable. So again, off to the sides if you need to see it, an x plus 2 squared. That means you're doing an x plus 2 times an x plus 2. And you can FOIL that. X times x will give you x squared. In the middle, I'll get 2x from the outer products. And in the middle, I'll get a 2x from the inner products. And last times last will, of course, give me a 4. But we're looking at x squared plus 4x plus 4. So that means when I go to subtract that whole thing, it's like there's a minus sign distributing in on all three. So you'll be subtracting x squared and subtracting 4x and subtracting 4. So that's where we are. Where's that going to take us? Welp, I see a 4 here at the beginning, and I see a -4 here, and so those are going to cancel out. Then what I also see, oops, we'll put a bar under that, is I see in the numerator here, with just these two terms left, I see an x that I can factor out. Really, I see a negative x I can factor out. So factor out a negative x, and that'll leave you with positive x plus 4. Then in the denominator I see this x. No, I don't. I see the 4 times x plus 2 squared. What I did see was this x, which is over 1, and I'm dividing by it. So multiply by 1 over x instead. I still think that's going to be the cleanest way to kind of break down these complex fractions. And I also notice that this x cancels with that one, so plugging in 0 now should not be an issue. So we now have the limit as x approaches 0 of negative x plus 4 all over 4x plus 2 squared. Yeah, that's it. So all we have to do is evaluate that now. So plug in 0, and you get negative 0 plus 4 all over 4 times 0 plus 2 squared. So it looks to me like in the numerator we're going to have negative 4. In the denominator we're going to have, yeah, okay, 4 times 2 squared, which is 4. Alright, let one of the 4's cancel, you get negative a quarter. That's your answer, negative a fourth. And we only have 2 more, so I want to hurry up. 14. I don't think there's anything special here exactly, just the denominator maybe. But I'm going to grab this guy again, 2x squared minus 17x plus 35. And off to the side, I'm going to factor this thing. 2 times 35 gives me factors of 70. So 1 and 70, no. 2 and 35, no. 3 and nothing. 4 and nothing. 5 and something? 14? That's still not giving me 17 though. Luckily, 6 might not divide in, but 7 does, 10 times. And if we're trying to be positive but with a negative sum, then it'll be negative 7, negative 10. And there's the 2 guys we're after. So again, the fast way to factor this is, you know it's a 2x, you know it's an x. The only number here you can get by multiplying by 2 is this 10. So I'll plop a 5 here and a 7 here. But that should work. And again, if you're not sure whether you factored correctly, just FOIL it. 2x times x is 2x squared. The outer product is a negative 10x, and the inner product is a negative 7x. And you get a positive 35 on the end. So at this point, if you can't see that you factored right, then I can't help you. But yeah, those 2 terms would give you the 17, so we're great. So let's grab this navy blue thing and substitute it in. So we now have the limit as x approaches 5 of 2x minus 7 and x minus 5. And now's a good time to notice and remember that we said if you want to switch the order of these terms around a minus sign, then just go ahead and do it. But remember that when you switch those around, you're now getting the opposite of what you used to get, which you can fix by just putting a negative sign on this. Now it's the opposite of the opposite, so it's back to being equal, and that's okay. Alright, so what's happening? Now that I've done that, I can cancel that and cancel that, and we see that we're just now evaluating the limit as x approaches 5 of, I'm going to bring this negative sign up, we'll say the opposite of 2x minus 7. So you just substitute in and get an answer. This will be negative 2 times 5 minus 7. Okay. So that's 10 minus 7, which is 3, but made negative, the final answer is negative 3. And one last problem, number 15. 15 is certainly looking like we have to multiply by the conjugate, but again, never know. Let's plug in 10, see what happens. 10 minus 10 is 0. 10 minus 1 is 9. Square root of 9 is 3. 3 minus 3 is 0. All right, no way around it. Got to use that conjugate. So we're multiplying by the conjugate of the term in the denominator this time. So that'll be 3 plus root x minus 1. And 3 plus root x minus 1. And in the numerator, we'll go ahead and just not simplify. So upstairs, we're going to leave it as an x minus a 10 times a 3 plus a root x minus 1. Now downstairs, we have to FOIL. Down here, we go 3 times 3 for a 9. The middle terms cancel, but my last term would be minus an x minus 1 in parentheses, because we're subtracting the whole thing. So what does that get us? 9 minus x minus 1, like that, would be a 9 minus an x. Okay, what am I doing? Oh yeah, we're just breaking down the parentheses. So plus 1, which would be technically 10 minus x. But I'm sure you noticed that we have an x minus 10 in the numerator, so let's flip these around again, remembering just to make it the opposite of what it used to be. So this is going to be the limit as x approaches 10 of an x minus 10, that's about to get canceled out, times our conjugate, the 3 plus root x minus 1. And in the denominator, we just have negative x minus 10, which we're going to cancel. So now we can substitute in. This is going to be the limit as x goes to 10 of, we've got this negative, may as well distribute it in up here. Our expression is technically just negative that whole conjugate. So let's distribute the negative in, call it negative 3 minus root x minus 1. But that should be pretty evaluatable. So plugging in 10 would give negative 3 minus root 10 minus 1. So that's negative 3 minus, well that's 9. Square root of 9 is 3. So final answer, negative 6. Okay, I hope that's it. Is anything missing from these problem sets? Not really. I'm just afraid maybe the ones we did were a little bit easier. But you've got this whole next set of practice problems. I don't even know if you guys can see these little watermarks I'm putting in. See the little Patriot guy? That means this was a mandatory problem. All these W's mean they're optional problems. And I don't think I see anything particularly nasty. And you've got all day Monday to ask questions if you want to. So let me see. Easy. Yeah, you'll figure that out. No big whoop. Looking good. Yeah, there's nothing crazy. So just do these other problems for practice if you need it, and ask me questions on Monday, and I'll be happy to help. But good studying. Be ready for Tuesday. Bye.